Hello and good evening to everyone. Today we're presenting page replacement algorithms in operating systems. We spoke about this in detail in the article. We'll be talking about its importance and some of the details we mentioned in the article here. This presentation um, of page replacement algorithms offers a comparative analysis of their performance characteristics, and we will explore various algorithms from foundational concepts of advanced adaptive strategies, examining their theoretical underpinnings, practical implications, and impact on overall system efficiency and responsiveness. Understanding the stakes, why page replacement matters. In an intricate architecture of modern computing, efficient memory management is paramount. Page replacement algorithms play a crucial role in bridging the gap between limited physical memory and the vast demands of virtual memory. Their effectiveness directly correlates with the system responsiveness and overall performance. Page faults cause costly delays. When a program attempts to access a page that is not currently in physical memory, a page fault occurs. These faults can range from minor inconveniences to significant performance bottlenecks. Particularly when they necessitate fetching data from slower storage devices like hard disk drives, HDDs, or solid state drives, SSDs. Such major page faults involve considerable I/O operation, leading to measurable slowdowns in system responsiveness and application execution. Efficient page replacement algorithm minimize page faults. The primary objective of any page replacement algorithm is to reduce frequency of major page faults by intelligently deciding which page to evac from physical memory when new pages need to be loaded. These algorithms aim to retain the most frequently or eminently used pages, thereby improving hit rate of the memory cache. Virtual memory relies on smart decisions. Virtual memory is a cornerstone of modern operating systems, allowing programs to access memory as if it were contiguous boundless space. This abstraction requires the OS to manage the dynamic mapping between virtual and physical addresses. When physical memory becomes full, the system must make a critical decision: which page to remove to make room for a new one. This decision, governed by the page replacement algorithm, is fundamental to maintaining system stability and performance. The page fault phenomenon, types and impacts. Understanding the nuance of page faults is essential for appreciating the role of page replacement algorithms. Not all faults are created equal. Their severity and impact on system performance vary significantly. Minor page faults. These occur when a page resides in memory but is marked as not present in the page table. For example, swapped out by another process or part of shared library that needs its page table and entry updated. The OS quickly resolves by updating the page table entry without requiring this I/O, resulting in minimal delay. They are typically fast fixes. Major page faults. These are the most detrimental type. They occur when the required page is not in physical memory and must be loaded from secondary storage, a hard drive, for example. This involves significant disk I/O, which is orders of magnitude slower than RAM access, causing considerable latency and directly impacting application responsiveness. Invalid page faults. These represent an attempt to a program to access a memory address that is not allocated to it or is otherwise invalid. This is typically a symptom of a programming error or a corrupted pointer. The OS responds by terminating the offending program, often leading to a crash or segmentation fault, and it signifies illegal memory accesses. The overarching goal of any effective page replacement strategy is to minimize the occurrence of major page faults, thereby optimizing the utilization of physical memory and enhancing overall system throughput. Classical algorithms, FIFO, optimal, and LRU explained. To understand the evolution of page replacement algorithms, it is crucial to first examine the foundational strategies that laid the groundwork for modern approaches. These classic algorithms offer varying trade-offs between simplicity, efficiency, and computational overhead. FIFO, first in, first out. This algorithm is conceptually simple. It affects the page that has been in memory for the longest time, regardless of how frequently or recently it has been used. It operates on the principle that the first page loaded will be the first one removed. While easy to implement, FIFO is known to suffer from Bilady's anomaly, where increasing the number of available memory frame can paradoxically lead to an increase in page faults, making it unpredictable under certain conditions. Optimal, often referred to as uh, Bilady's optimal algorithm. This strategy replaces the page that will not be used for the longest period in the future. It guarantees the absolute minimum number of page faults for a given reference string and frame count. However, its practicality is limited because it requires foreknowledge of future page accesses, which is generally impossible in real world scenarios. Despite its impracticality, the optimal algorithm serves a crucial benchmark for evaluating the efficiency of other algorithms. LRU, least recently used. LRU operates on the principle of temporal locality, assuming the pages that have not been used for the longest duration in the past are likely to be used in the immediate future. It affects the page whose last access in a time and is furthest in the past. LRU is generally considered a good balance between performance and feasibility, offering significantly better performance than FIFO and closely approximating optimal in many workloads. Its widespread use stems from its effective exploitation of typical memory access patterns, although its implementation can involve higher overload for tracking access times.
Good morning, good evening, depending on the time you're watching this video. My name is Abdulkadir and I'm gonna carry on with visualizing classic algorithms behavior. To illustrate the performance differences between these classic algorithms, let's consider a practical example using a specific page reference string and a fixed number of memory frames. These demonstrations highlights how each algorithm makes a eviction decision and the resultant number of page faults. Consider the following page reference string and a system with 4 available memory frames. We have our string over here. Let's analyze the number of page faults generated by each algorithm. We have FIFO with 8 faults and optimal with 6 faults and LRU with 7 faults. As observed in the example, the optimal algorithm consistently achieves the fewest page faults, setting the theoretical benchmarks that other algorithms strive to approach. LRU typically performs well, often coming close to the optimal algorithm's fault rate due to its reliance on past usage to predict future needs. And FIFO generally exhibits the highest number of page faults, largely because it discards page based solely on their entry time, ignoring crucial usage patterns These inherent limitations makes FIFO less suitable for workloads where recently accessed pages are frequently re-referenced. We have our example over here. Calculate the page faults using FIFO, LRU, and optimal algorithms. Page replacements algorithms for the following reference string for memory with 3 frames. This visual comparison underscores the importance of intelligent eviction policies in minimizing page faults and maximizing memory efficiency. And let's continue with advanced algorithms beyond the classics. While classic algorithms like LRU provide a solid foundation, modern operating system and complex workloads demands more sophisticated page replacement strategies. Advanced algorithms often incorporate heuristics to approximate optimal behavior with practical overheads or adapt dynamically to varying memory access patterns. Let's continue with our first algorithm, is clock algorithm. The clock algorithm, also known as a second chance, is practical and efficient approximations of LRU. It uses a circular list of pages in memory, each with a reference bit. When a page is referenced, its bit is set to 1. During page eviction, the algorithm scans the list, clearing references bits. If a page's bit is set to 0, it's evicted. If 1, the bit is cleared and the scan continues. This provides a second chance for recently used pages, offering near LRU performance with lower overhead than true LRU, making it ideal for large memory system. We have our second algorithm over here, ARC, Adaptive Replacement Cache, developed by IBM. ARC is powerful algorithm that dynamically balances recency and frequency of page access. It maintains 2 lists, one for page recently seen but not frequently accessed, and another for frequently accessed pages. ARC adapts its policy based on workloads patterns, achieving superior performance by recognizing both temporal and spatial locality. Studies have shown it consistently outperforms LRU and clock on diverse workloads by avoiding their common pitfalls. And our third algorithm is LIRS, or Low Interreference Recency Set. Is a more complex algorithm that aims to capture inter-reference recency more accurately than LRU. It tracks the recency of both resident and non-resident pages to determine their reuse distance. LRIS is particularly effective in workloads with varying access patterns, such as database systems, where some pages are accessed very frequently, while others are only occasionally. It's adaptably allows it to make more informed eviction decisions, especially in systems with heterogeneous memory demands. And our fourth algorithm over here is CAR clock. It's called CAR. It's clock with adaptive replacement. CAR combines the simplicity and efficiency of the clock algorithm with adaptive capabilities of ARC. It builds upon clock's mechanism, but incorporates ARC's strategy for dynamically adjusting the balance between recency and frequency. This hybrid approach allows CAR to achieve high performance with relatively low implementation complexity, making it an attractive choice for operating systems kernels that require robust and efficient memory management without excessive overhead. And over here we have comparative performance insights. Empirical studies and simulations consistently demonstrate the performance advantages of advanced page replacement algorithms over their simpler procedures. These insights are crucial for system architects and developers in selecting the most appropriate strategy for specific computing environments. We have here a loading bar for reduced page faults. Research indicates that adaptive replacements, cache or arc, and the clock with adaptive replacement or core algorithms can reduce page faults by 10% to 30% or more compared to traditional LRU in real world benchmarks. And diverse synthetic workloads, this significant reduction translates directly to improved applications performance and overall system responsiveness. And in second chart over here we have clock efficiency. The clock algorithm, while simpler than full LRU implementations, provides performance that is typically within 5% of LRU efficiency, but with considerably lower computational overhead. This makes clock an excellent choice for system where minimizing overhead is crucial, such as embedded systems or operating systems managing very large physical memories. And the third one over here we have LIRS advantages. Low interreferences, recency set or LIRS has shown particular strengths in workloads with poor locality characteristics, such as database access patterns, where it can outperform LRU by up to 15 or 20% in terms of page fault reduction. Its ability to track and differentiate between frequently and recently accessed pages allows it to adapt to complex memory usage patterns more effectively. And the superior performances of advanced algorithms stems from their ability to better understand and predict memory access patterns, especially in the context of modern software that exhibits um, the chaotic and unpredictable memory access behaviors. Unlike static policies, adapt algorithms dynamically adjusts their eviction strategies, leading to higher cache hit rates and more efficient use of physical memory.
Good day, everyone. My name is Ali Samir. I'm here to continue the presentation. Okay, we're going to talk about real-world implications and challenges. The theoretical advantages of advanced page replacement algorithms find significant applications in the design and optimization of contemporary operating systems. However, their integration also presents unique challenges. Okay, let's talk about adoption in modern OS kernels. Operating systems like Linux and FreeBSD have evolved to incorporate sophisticated memory management units (MMUs) that leverage variants of advanced page replacement algorithms. Specifically, both kernels utilize modified clock algorithms. An example, the 2Q clock variant of Linux, or a similar multi-list LRU approximation in FreeBSD. For their unified memory and the file caching mechanisms, this allows them to effectively manage both application data and file system caches within a single memory pool, optimizing resource allocations and reducing redundant data in memory. Those kernels continuously refine their eviction policies to adapt to varying workloads from desktop application to high performance servers, demonstrating the practical efficiency of these algorithms in production environments. So here's the graph that talks about adoption in modern OS kernels. Okay, now let's talk about challenges in implementation, scalability. As physical memory sizes continue to grow from gigabytes to terabytes, the overhead of track and page usage for algorithms like LRU, which may require frequent updates or to timestamps or explicit linked lists, can become prohibitive. Advanced algorithms must be designed for scalable performance across vast memory landscapes, Workload complexity. Modern applications, with their intricate dependencies and dynamic memory access patterns, pose a significant challenge. Workloads can be highly varied, ranging from sequential streaming to random access, requiring algorithms that can adapt rather than rely on fixed heuristics. Balancing complexity and fault reduction. There is an inherent trade off between the complexity of an algorithm and the gains it provides in fault reduction. A highly complex algorithm might offer marginal improvements in fault rates but introduce significant CPU overhead. Getting its benefits, system designers must carefully evaluate this balance, often opting for algorithms like clock or car that provide good performance with manageable overhead. Now talking about summary, uh, choosing the right algorithms. Here we have four algorithms. Number one, we have optimal algorithm, the theoretical gold standard, providing the minimum possible page faults, while impractical for real-world implementation due to its requirement for future knowledge. It serves as an valuable benchmark for evaluating the effectiveness of other algorithms. It helps set performance ceilings. Number two, we have first in, first out. Remarkably simple to implement, first in, first out is appealing for its low overhead. However, its tendency to evict frequently used pages and susceptibility to Bilady's anomaly makes it generally inefficient for typical workloads. It's primarily suitable for education contexts or very simple, non-critical systems which memory access patterns are highly predictable of it. Number three, LRU, or least recently used, a practical and generally effective algorithm that leverages temporal locality. LRU often provides significantly better performance than first in, first out. However, its exact implementation can be costly, especially in systems with large numbers of pages, due to the need for precise tracking or access times or maintaining complex data structures. This overhead can become a bottleneck in highly dynamic environments. Clock and Arc family. These algorithms represent the best trade-off for modern operating system needs. Clock offer near clock clock offers near LRU performance with reduced overhead, making it widely adopted. Arc and its variants like CAR further enhance performance by dynamically adapting to workload characteristics, balancing recency and frequency. They are robust choices for complex, dynamic memory workloads, offering high fault reduction with acceptable implementation costs. The future of page replacement algorithms. As computing environments continue to evolve, the demands on memory management and thus on page replacement algorithms will become even more stringent. Future research and development are focusing on increasingly sophisticated and adaptive approaches to maintain optimal system performance. Machine learning for reduction. A burgeoning area of research involves applying machine learning techniques to dynamically predict future page usage by analyzing historical access patterns and system state. ML models could potentially make highly accurate eviction decisions, leading to fault rates closer to the theoretical optimal. This approach promises a paradigm shift from heuristic rules to data-driven intelligence. Hybrid algorithms. The trend towards hybrid algorithms will continue, combining the strength of various strategies. Future algorithms will likely integrate concepts of frequency, recency, and workload contexts more seamlessly, perhaps even adapting their internal parameters based on real-time system feedback. This would allow for a highly flexible and efficient memory management solution across a broader spectrum of applications. Evolution of memory hierarchies. With the advent of non-volatile memory (NVM), tiered memory architectures, and increasingly complex caching layers. Page replacement algorithms will need to adapt to these new realities. Decisions will involve not just eviction from RAM to disk, but also migration between different tiers of memory with varying performance characteristics and costs. Ultimately, as memory hierarchies become more complex and workloads more dynamic, intelligent page replacements remain a critical pillar for ensuring operating system efficiency, application responsiveness, and an optimal user experience in the future of computing. Okay, guys, that was our presentation. Have a good day.